Have you ever wondered if you, yourself, could measure the actual, repeatable distance to the moon? Back in the summer of 2015, after a considerable amount of research that I was doing for an upcoming book project that I was writing, I personally wondered exactly that. My initial reasoning was, no. I mean, how could I, a simple country guy from a small semi-rural town in Ontario, Canada, ever manage to concoct a simple but accurate way to measure lunar distance? NASA, with all of their billions of dollars in assets and expensive laser equipment, already confirmed the distance to be about 240,000 statute miles, depending on the apogee and the perigee at the time the measurements were taken. Like most things that I set about to accomplish, I like to start with a working model. I reckoned that if I started small with something that could be double-checked by physical measurement after the calculations were complete, that perhaps the same concept could be expanded upon on the larger lunar measurement. Let's start with something simple to test the idea. My thinking was, what about a flagpole? If I could locate one that could be tilted over by removing a pin, then the height of the object could easily be checked against my calculations. The necessary equipment to perform this part of the experiment is most likely already in the experimenter's existing arsenal of items that they already possess. A pad and pencil, a calculator, a measuring tape, a yardstick, a level, a couple of C-clamps, a school protractor and a tripod is all that is required. The experiment. Set up the tripod a workable distance from the chosen flagpole. Clamp the carpenter's level on the top plate of the tripod, set the bubble to level and sight in the flagpole. Mark the flagpole where the level sighting intersects the pole. Clamp the end of the yardstick to the end of the level, the end furthest from the flagpole. With the bubble of the level remaining perfectly horizontal, adjust the yardstick to align with the very peak of the flagpole. This establishes the angle of inclination, as I prefer to call it. Thus, a right-angled triangle is created when viewed from the side of the experiment. The carpenter's level establishes the baseline, the flagpole itself represents the right-angled vertical, y-axis, and the yardstick equals the hypotenuse of the aforementioned triangle. If we know any two parameters of a triangle, we can usually calculate the third unknown quantity. We can easily physically measure the distance of the point where the yardstick and level intersect to the flagpole with an appropriate tape measure. We can place the school protractor against the yardstick level device to read off the angle of inclination to the top of the flagpole, so we therefore have two factors that are known. Calculating the y component, then, the flagpole height, is pretty straightforward. Here are some sample measurements. Yours may vary, of course. Keep in mind we are attempting to establish this working model as a base for the larger lunar measurement experiment to follow once a strong and solid foundation for the approach is well understood. In my own example, I measured the angle of incidence to be equals 32 degrees, measured from the protractor. The baseline was established at 102 feet exactly. This is a right-angled triangle with the unknown being the height of the flagpole, minus the level sighting mark to the ground. In trigonometry, don't be afraid of the term. The tangent of an angle in a right-angled triangle is the opposite side divided by the adjacent side. The opposite side in our little experiment is the flagpole height, which is presently unknown. Let's call it P, for pole. The baseline has been measured at 102 feet. Let's call this B, for baseline. So, if tan 32 degrees equals P, B, we can rearrange the formula for the unknown. Thus P equals tan 32 degrees by B, baseline. Tangent table can be found in most math books, but the simplest way is simply to ask Siri or just Google it. Put tangent of 32 degrees into Google. The answer is 0.624869359 rounded off to 0.62, therefore P equals 0.62 x 102 equals 63.24 feet. Is this the height of the flagpole? Close, but no cigar. We still have to add the distance from the sighting mark that we placed on the pole, to establish eye level, to the ground. When the 63.4 feet was added to that number, being 5.5 feet, the final result is 68.74 feet. When the pole was tilted over and measured directly, the value obtained was 68.66 feet. The reason that I feel it is so vitally important to understand this simple flagpole experiment is that it establishes an accurate way to measure distant objects in height without having to climb the object or use tape measures that are extremely long to obtain the desired results. My suggestion now, is to back up or replay the video and go over the flagpole model again until you fully understand just how this experiment works. When it is crystal clear in your mind, then go to my website at www.barryhowardbegley.com, then go to the What If section and go down to the number 7 What If. All the information is there on just how to use this example to complete your lunar distance measurement. Good luck and please keep in touch with your results. Please consider one of my many books sold on Amazon worldwide for this and many more experiments of interest.